Not yet.
Oh,
Now go.
hey, magic. Here we go. So here we start then. Hopefully you can hear me and everything this time. And we're going to play the fundraiser. We're running out of money. So please give us money so we can carry on with everything. Okay, Franklin, please play the.
Hello, my name is David Hilser, and I'm president of the John Chappell Natural Philosophy Society. Our organization is unique in the world in that we allow for serious criticisms of mainstream science from physics to cosmology and from math to philosophy. And today, this organization resides 100% online. If you enjoy our Saturday morning talks, our websites, and the community of amazing critical thinkers you can interact with on the internet, then please consider contributing to our annual fund drive. It costs almost $3,000 per year to keep our internet presence and our Saturday morning talks alive and well. I want to thank all of our members who pay monthly and annual memberships, which is vital to our day-to-day operations. But unfortunately, this is not enough, and that's why we're looking to raise $2,000 in our 2024 drive. So if you don't want this organization to disappear, and you think that its mission is important, then please consider donating to the CNPS. It's vital to keeping science moving forward. Please go to fund.naturalphilosophy.org and donate today. Thanks once again from all of us at the CNPS. Your donation is vital.
Hi. Hello, everybody. I think I'm back now. So please help us to carry on by with these alternative physics talks and promoting such issues as Einstein's relativity has mistakes in it. So I'm going to my slides now, hopefully. Present slides. Here we go. So let me know, Franklin, if you still hear me. So we're going to go through the slides now. And this is anti-relativity session 7, dealing with the contradictions in the twin paradox. So this is roughly the setup for the twin paradox, where you have two twins. One twin goes off on a spaceship and the other stays at home. When the space traveling twin returns, the twin on Earth has aged more than the space traveler. Less time happened for the space traveler. When you go into you can start arguing about the details about this. The details can be argued about. Is there a preferred frame involved? Can acceleration be ignored? And is it just an effect on the clocks and not on time itself? And arguing over, is there really an aging effect involved? So there's a lot of ambiguity in there and a lot of things to argue about. So from my perspective, it still remains the problem of what is Einstein's relativity. It's something that has undergone numerous changes and reinterpretations. Einstein's special relativity started 1905 with this paper on that, and it means there's over 100 years of literature on relativity. Thus, it's a vast subject to go into, so it's very difficult to go into everything about it. For those pro Einstein relativity versus those anti-Einstein relativity, those that are pro seem to like to give the false front that there is only one solution to the twin paradox from relativity when actually they're giving conflicting and often contradicting solutions to it. And so, in my view, those people who are pro Einstein relativity are not really playing fair. So that now, with the internet, there are many videos about the twin paradox, and in my view, many of them are contradictory. So you can watch these videos on twin paradox, and they're starting to contradict each other. So this is the video I want to play, and it's called Dr. Lincoln is Wrong about the twin paradox. Oh, what's going on? We're not gone to the video, so we can play the video now.
Recently, I was searching for twin paradox videos on YouTube just to see how other people on a platform solved it, so that I can bring something new into the topic or explain it in a different way. And I stumbled across this video from the channel Fermilab with the name of Twin Paradox: The Real Explanation. The video is very well made, there is a math involved, and it's made by professional, so no one would actually dare to question it. But with all due respect to the Dr. Lincoln, I don't think the explanation is very real, nor I think it's explanation of a twin paradox at all. So what is the problem? Dr. Lincoln claims he can solve the paradox without acceleration by introducing not 2, but 3 observers A, B, and C. He introduces 3 locations, 1, 2, and 3, that are separated by distances L and 2L. And then he places observer A and B to the first location, and the observer C to the third location. The observer B is moving with the velocity v to the right, and the observer C is moving with the velocity minus v to the left, and all observers have initially 0 on their clocks. And now the most important thing. This initial configuration was set in a rest frame of the observer A, and therefore, in order to figure out the coordinates of other observers, we need to use the famous Lorentz transforms. And this is how it plays out according to channel Fermilab.
So here's what we're going to do. When we start the experiment, all 3 observers are going to start a stopwatch. When observer B and C cross paths at the center, observer B holds up a big digital clock that observer C can read. That clock records how long it took for observer B to go from location 1 to location 2. Observer C also writes down the time they see on their own stopwatch as they cross location 2. Observer C then travels back to position 1. As they pass location 1, they hold up a big digital billboard that shows the reading on their clock as they pass location 1, the reading on their clock as they pass location 2, and the amount of time it took observer B to get to location 2. You can then work out the amount of time it took observer C to get from location 2 to 1 and add it to the amount of time that observer B took to get from 1 to 2.
Okay, that feels pretty logical, but how does this situation plays out if we actually show the clocks? The time dilation equation is simple. It doesn't depend on the orientation. So, from the reference frame of the observer A, the observer B and C get the same time dilation, and therefore at the meeting point, their clock will read the same time. And now, the observer C should read the clock of the observer B and continue his journey towards the observer A. Then at the meeting point, we just add the second part of the observer C's clock and the screenshot of the observer's B clock. And we have the total time for the traveling observer, which we can compare with the observer's A clock. But this part here is actually exactly the same as this part. So you might ask, why we even need the observer B? The whole situation kinda reduced to a simple time dilation problem. But this is not the end of the video, so let's take a look at the calculations. According to Lincoln, there are three important events we have to take into account. Event 1, the moment observer B departed from Earth, the meeting point, and the second meeting point at the observer's A location. Now we can figure out the space-time coordinates of these events for each observer. And of course, the simplest observer to consider is the observer A, as the whole configuration was set in his rest frame. So the spacetime coordinates of the event 1 is just 0, 0, which is just by definition. The second event happens at the position of L and time L over v, as the classical equation for time, distance, and velocity says. And the third event happens again at the position of 0 and the time of 2L over v. And this is exactly what Dr. Lincoln proposes. Okay, now it gets a little trickier when we consider the observer B. The event 1 is still easy though. The position is 0 by definition, and time is also 0 by definition. To find out the spacetime coordinates of the second event, we can use the coordinates of the observer A and use the Lorentz transforms. Here the math is a little bit involved, but still very simple and also exactly what we would expect. The position is 0 since the observer B is exactly at the location of the event, and time is reduced by this gamma factor, since the length he traveled in his coordinates is shorter due to length contraction. For the event 3, if you do the math, you get this, which also agrees with the numbers of Dr. Lincoln. But now it gets really tricky if we consider the observer C. According to Lincoln, the space-time coordinates look like this. Event 1 happens at the space-time position of 0, 0, but if you look at the picture, this doesn't seem to be correct.
Energy supplies don't want you to know about this trick to warm up houses for practically zero cost. This space heat.
In special relativity, every observer is maximally selfish and considers himself as a center of the whole universe and stationary. And therefore, this third observer should have spatial coordinate at this position be 0. And therefore, the coordinate at the position of event 1 has to be something else. And what about time coordinate? I told you the whole configuration was set in a rest frame of the observer A. And for this observer, the observers B and C departed simultaneously at time equals 0. But from my previous videos, you already know that simultaneity is relative if you have a spatially separated events. So if these two observers departed at the same time for the observer A, this can't be true for the observer C, since they are spatially separated and moving relative to each other. So let's take a look at the simultaneity planes for these two observers. This is the simultaneity plane for the observer A, when observer B and C simultaneously departed. Then if you take the velocity of the observer C, for example 0.87 c, then his coordinates would look like this, and this is his simultaneity plane. So as you can see, at the time 0 of the observer C, the observer B has departed a long time ago, and therefore it can't be 0 as Lincoln proposes. The problem is that Lincoln used these Lorentz transforms to get his results. But the problem is that these Lorentz transforms apply only to observers who started at the same location. And that is why it worked well for the observer B, but not so much for the observer C, since there is no information about the initial spatial separation. The question is, what are the full Lorentz transforms? And the only thing you have to do is a small modification, where this term here is the difference between the position you are transforming to and your position. So let's figure out the correct coordinates of the observer C with these upgraded transforms. So for the event 1, the coordinates for the observer A is just 0, 0. And if you plug it into the transforms, this is what you get. And it was pretty simple. For the second event, the calculation is more involved, but in the end, you get the result you would expect. The position is 0 as the event is at the same location as the observer C. And the time on his clock is exactly what would you get using the length contraction. And finally, for the event C, you get again expected result, since the event is again at the same position as the observer C and the time according to length contraction. So now you can do the same business calculating the time interval between event 2 and 1 for the observer B, and add to that the time difference between event 3 and 2 for the observer C. And you get the same thing that has already been on the clock of the observer C. And suddenly, the explanation of a twin paradox doesn't seem to be anything more than just a time dilation problem. Natural question, however, is that since time dilation is symmetrical, then if you look at the problem from the observer C's perspective, the distance is shorter, and moreover, the observer's A clock is slower. How can the observer A be older at the meeting point? And this is classical clock synchronization problem. If you make the separation 20 light years and velocity of minus 0.87 c, then if you look at the space-time diagram, as I already showed you, for the observer C, there is already 17.4 years on the clock of the observer A. And now, since the distance for the observer C is just 10 light years, it will take him 11.5 years to reach the observer A. But the clock of the observer A is slower by 2, and therefore it will add only another 5.75 years to the observer's A clock, making it roughly 23 years, as it should be. There are many questions you might ask. For example, since for observer C, the observer B has departed a long time ago at his time 0, how it is possible they meet near the star if they are moving with the same velocities towards it? And the answer is, in a way, we add velocities in special relativity. For the observer C, the star is moving with the velocity 0.661 c towards him, but the observer B is moving with the velocity given by this formula, which gives you roughly 0.9898 c. Here, be very careful to use very precise numbers when adding velocities in special relativity, because rounding can actually bring a big error in your calculations down the road. I used the velocity of 0.8661, so the gamma factor is roughly 2. Now you can subtract the velocity of the star from the velocity of the observer B, and you get the rate at which the observer B is approaching the star in a reference frame of the observer C, and it is just 0.1237 c. The distance the observer B has to travel in the reference frame of the observer C is 5 light years, and therefore the whole journey should take 40.42 years. But if you remember the space-time coordinates of the first event for the observer C, you will find out that the observer B has departed 34.67 years ago in the reference frame of the observer C, and it will take him another 5.75 years to reach the star. This is exactly the same time as it will take the observer C to reach the star, and therefore they will reach the star at the same time. And of course, the gamma factor for the observer B is 7.02, and if you take the time of 40.42 years and divide it by this number, you get 5.75, which is the observer's B clock's reading at the position of the star. It's always nice to see the numbers eventually add up perfectly when you do the calculations correctly. Notice one crucial thing. When I calculated the speed frame over C, I had to use the relativistic addition formula. However, When I calculated the rate at which the observer B is approaching the star in the frame of the observer C, I used classical addition formula. The reason is that when I calculated the approaching rate, I used the velocities as measured from the same reference frame, namely C. In the other case, I used velocities as measured by the observer A in the frame of the observer C.
Have hassles ruined your holiday in the past? Introducing Holiday Extra's new Hassle.
I wanted to briefly mention this because I have encountered people who see no difference between these two cases. Okay, enough of numbers. There is another thing I disagree with Dr. Lincoln.
All of the time dilation, which is to say the shortening of the time experienced by the traveler, occurs during the acceleration periods. However, this explanation is totally wrong. Now, if you thought this was the explanation, don't feel bad.
So the twin paradox is made of two parts, the outgoing journey and ingoing journey. And this makes 100% of the trip. Time dilation is symmetrical, and therefore, during 100% of the trip, both observers can claim to be perfectly stationary and see other clocks running slower. So, how can we make one observer younger eventually? If there is a true time shift somewhere, it must have happened continuously, right? Because nature is continuous. The only thing we left out from the story is the acceleration part. And therefore, if there is a true aging happening somewhere, it must be happening during this part. Otherwise, there is just no any other time period where this could happen. So saying the acceleration is not responsible for the aging in twin paradox is completely false. And I will explain it hopefully in the next video. In this video, I want to thank people who bought me coffees on
So that's the end of that video. I'll get back to the slides. So back to the slides, and the video that the speaker was criticizing was by Don Lincoln. And Don Lincoln is an American physicist, and he's taken it upon himself to educate us about relativity. And the person criticizing Don Lincoln is supposedly another expert on physics. So this is what the person says about himself. He says he's Lucas, and he's a PhD student on theoretical physics. So they're disagreeing. In my view, normally doesn't happen where you have two physicists who are openly disagreeing about relativity. What normally happens, in my view, is physicists try to pretend there is no disagreement in relativity among themselves. They might say contradictory things and compare what one says with what another one says, but they normally ignore what another person says that contradicts what they say, thus enabling them to present the false front there is no disagreement in relativity. If we go back to this person, and it's Herbert Dingle, who lived between 1890 and 1978. He was an English physicist and philosopher, and he served as president of the Royal Astronomical Society. And after initially accepting Einstein's relativity, he then started criticizing it. And in this book, he's criticizing Einstein's relativity. In particular, he's criticizing the twin paradox, pointing out that the twin paradox did not make sense because there are those who believe in Einstein's relativity who would give different solutions to it. The response of the pro-relativity people was to mostly ignore the issue and carry on regardless, presenting the false front that they were all united in believing one solution, the same as they try to do today. Except now two people pro-relativity have presented videos where they disagree to the solution of the twin paradox. And it's these two people. Right, so that's basically the issue which I'm pointing out in relativity, that it is quite a mess when you actually go to the twin paradox. You've got disagreement in what's going on. So you haven't got a properly defined theory. It's just a mess of conflicting opinions as to what's going on. So thank you. That's the end of this little talk. We can now open it up to discussion as to what we think about that. Thank you. You can come back now, Franklin. Can you open it up, please? Thanks. Okay. Excellent. Okay. Hi, Franklin. Are you there? Hello.
Yep, I'm here.
Hi. I can't see you. Can you share? Do I have to just press share screen or something? Stop screen, is it? Okay.
No, you're fine, Roger.
I can't see you.
So it looks like perhaps maybe Nick. Nick, are you raising your hand there?
Yeah. Hello.
I'm not quite sure. Are you there? Well, I'm going to put up Nick. I think Nick is trying to tell us something.
Yes, please. Try put him up. I can only see myself. Oh, great. Excellent. That's it. Got to see it.
Can you hear me?
Yes.
We can hear you now.
Okay.
Oh,
I think it's great to go through the twin paradox and make the point that Roger is making. But since the twin paradox can have 7 different explanations, and all of those explanations can have strong arguments one way or the other, I just wanted to make the point that if you look at 2 clocks in outer space that are moving relative to one another, and then you try and determine what is the physical meaning of the special relativity time dilation equation, you quickly realize that you cannot interpret the time dilation equation as calling for physical slowing of clocks. Because let's say, otherwise, as Dingle pointed out, since A and B, there's no difference between them. Neither is accelerated in their past history, let's say. Both would determine that the other clock is slower, and that's not only counterintuitive, but it's counterlogical. You can't have A's clock slower than B's clock, and B's clock slower than A's clock. So that's a pretty clear-cut explanation. But I think what's very interesting about what Roger is going through is that all of these different explanations for the twin paradox show that the person who is pro-relativity isn't using critical thinking because they just overlook some very obvious problems in their reconciliation argument. So at the moment, that was the one point I wanted to interject.
Yeah.
Thank you.
Thank you. Yeah. Those that are pro relativity all sort of like believe different things. So they haven't got a properly presented theory, which is a nuisance. If you're trying to find a replacement to Einstein's relativity, you face the problem that the people that support it all believe different things. And they're not properly explaining a proper solution to the twin paradox. They're presenting lots of different solutions. So that's not fair. They're just not playing fair. It's sort of like it's a two-way process. A person who's presenting the theory has to properly explain that theory, and then you can decide whether it's right or wrong, and then just present a different theory if you think it's wrong. But when it's just ambiguous the way that special relativity is, they're not playing fair. You don't know what you're dealing with. So it's wrong from the very beginning. They've broken the scientific process by not presenting a properly defined theory. So that's the educational process, and educational process of teaching relativity is just completely messed up. And then when you want to say, well, it's confirmed by experiments, it's totally ambiguous as to what they've really done. The person doing the experiment, they can all believe in different things. Okay, is you back there, Franklin? Is there any? Franklin? Oh, great. Back again.
Yes.
Thank you. Okay. Thank you, Nick. Cheers. Thank you. Is there anybody else? Hi, Franklin. Can you hear me?
Yeah. So where would you like to go with from here? You know, we have a few comments going on here.
Okay. Read out a few comments then. Thank you.
I mean, you know, Andrew is kind of, you know, wondering, you know, what your philosophy is on doing this video. So perhaps you can motivate, you know, why you were showing that video. To me, you know, I commented that, you know, they lost me at, you know, after the word "the." So when they started launching into this different situation, and it's like well, I just have to say I was lost.
Yeah.
I got nothing out of it.
Yeah. When initially the people that believe in Einstein's relativity, when they want to come to the public and talk about it, want to present something very simple to understand. But then when you look into the thing in more detail, then it gets even more confusing. And then the people that are believing in Einstein's relativity then come up with all their excuses, and they put their add-ons onto it, add extra bits onto it. So you've got Don Lincoln, who came on, all happy and jolly, explaining twin paradox in what he thought was an easy to understand way. And then you got this other person come on with a video criticizing that video, and that just complicates the subject. The subject is being falsely presented as something easy to understand and very simple to grasp the basics of, but it's just really a confusing mess of people with lots of different opinions, and so they're not presenting the subject properly to people, pointing out to them that the subject is a complete total mess, And that was the sort of aim of presenting this video on the twin paradox. It just turns into a total mess.
Yeah, I mean, your comment was that,
Yeah.
this video is just a confusion of math.
Yeah.
So was
Yeah.
your point in showing this?
Well, when you start talking to ordinary people, you, as an educator, you're trying to present something non-complicated, and so you are easy to understand. So you don't want to go into complicated maths, but in the end, they just try to cover everything up in complicated maths, and the general public just gives up in the end.
I mean, that math though in there, that was even more complicated than normal.
Yeah, that's what you end up with if you try to go into the twin paradox in more detail. It just ends up in a confusion of complicated mathematics, and that's when the general public switches off. Most of them, those that don't appreciate mathematics, or who have problems with understanding mathematics, it deceives people to believe something because, well, they say, well, the maths is there for it, so therefore I believe it. But actually, they don't understand the maths. The general public don't understand the maths. So, so the physics establishment is trying to deceive people by pretending it's an easy to understand subject.
Well, what is your opinion on this video? I mean, you've got two physicists here.
Yeah.
And I'm not even sure. You got the younger physicist guy and you got the older physicist guy, Don Lincoln.
Yeah.
And what was the younger guy trying to say? That Don was still not explaining things correctly?
He criticized Don Lincoln's explanation for the twin paradox. So Don Lincoln offered his solution, and this young guy, he criticized that. He didn't believe that solution. So this is what you get at sort of like physics conferences. When you're discussing physics, you get disagreement about things sometimes.
Well, was either of them right, or were they both wrong?
Just confused. Well, relativity is just confused math. If you go for me personally, I go back to Einstein's original paper in 1905, and I say it's not been translated properly from German into English. So you've got the problem of, are people going by the bad translation of Einstein's paper, or should we be going by the proper translation? And in my view, that's two different theories. So it completely goes wrong at the very beginning. And if you try to understand it, well, Einstein, you try to understand that paper of 1905, well, Einstein does present things like the principle of relativity and the idea of the constancy of the speed of light. But if you look into the mathematics, it looks like, well, he's got light speed as not being constant. So the mathematics is contradicting what he's saying. He's saying light speed is constant, but the mathematics says the opposite. And then when he's talking about the principle of relativity, the principle of relativity in simple terms means there's no preferred frame. But then when he goes into the mathematics of it, and he's dealing with clocks, well, he sort of brings it in a preferred frame. He doesn't say he's bringing in a preferred frame. It's an unstated preferred frame. And the clocks he's dealing with are from a preferred frame. And so he's abandoned the relativity principle. And so that's the contradictions in his initial paper on relativity, is all just contradictions. And that's what people have built upon.
Well, let's get to something a little bit more solid, which is experimental evidence. So we have some comments from Andrew Castro, who's apparently a particle physicist who does a lot of work with accelerators, and he asked this question of, why don't we just start with those accelerator experiments and show how, we see true experimentally confirmed decay time changes. So what do you think of, actual experiments which actually demonstrate things like time dilation?
Well, when you get to physics, you've got the physics divided into different groups. You've got the educators, you've got the theoretical physicists, and you've got the experimenters. And to the students, the educators are presenting the theory of relativity. And when it comes to the experimenters, the papers I read, they don't really generally they talk about the experiment, the data, and so forth, but they don't explain what do they believe is the theory of relativity. So they're not educating you as to what the theory of relativity is. And so those people who are writing these papers, they all believe in different things when you talk about the theory of relativity. Because as the example I gave a long time back in one of my videos, Don Lincoln considered himself working on the experiments of relativity, and he's saying from those experiments there is no relativistic mass. And that's contrary to what a lot of the educators have been doing. They've been teaching there is relativistic mass. So you've got the split between all these different groups, educators, theoretical physicists, and the experimenters. They're just not making it clear what they believe is the theory of relativity when it comes to doing experiments, and whether it agrees with what the educators are saying. So it's total ambiguity on the subject. You need the theory clearly explained, and they're just not going to do that. They're just going to have a collection of different opinions where they're all saying different things and believing different things.
Okay, it looks like Nick wants to come back, so let's add him back here.
Yeah.
Yes, I'll try to answer Andrew's question more directly, I guess.
Mm-hmm.
At CERN, John Field, I don't know if he's still alive, but recently he was still alive, was the expert on particle half-life decay as a function of velocity. Now, he remained a relativist, but he didn't like the fact the data that he was messing with led him to throw out relative simultaneity. And he found that the data at CERN regarding half-life decay was accurate if you used the Earth-centered inertial frame as the base frame and measured velocity with respect to the ECI frame. And the farther, if you chose another frame, another inertial frame, to be the base frame, as special relativity claims you should be able to do, you find that the data does not match those views from other frames. And the more that the other frame differs from the ECI frame, the further away you get from matching the CERN data on half-life decay. In addition, Ron Hatch, who had 30 patents and 30 plus patents for GPS, said that the GPS data shows that quote unquote time dilation, but what she referred to as clock retardation, matches calculating the effect using velocity, absolute velocity with respect to the GCI frame. And if you used another inertial frame as the base frame, as SR, special relativity claims, then you get wrong answers, and GPS would not work. It would direct people into lakes, et cetera, et cetera. So the empirical data, particularly from GPS, which is very high precision, shows that you cannot use the special relativity interpretation of the time dilation equation. It's really more like Lorenz's original clock retardation equation, where velocity is absolute velocity with respect to a single preferred frame. And at least in the vicinity of the Earth, for both particle accelerators and GPS, that single preferred frame is the ECI frame. Thank you.
Thank you.
Yeah, I think that's an important point that really gets glossed over here. So you're saying, Nick, that if you do the careful experiment on the accelerator, you find you're using Lorentz preferred frame theory, where
Yes.
the Earth inertial frame is the preferred frame. Experimentally, that's what we observe. But I think most physicists say that, no, we're using relativity. And what they're using is that they're using the Lorentz factor, which is in Einstein's paper, which he borrowed or misappropriated.
Mhm.
And because that formula works, people claim that relativity works. And yes, relativity does work, but Lorentz's version of relativity works, not the symmetrical version of relativity that Einstein's paper is trying to promote.
Right, and Lorenz's version is non-relativistic. It's 100% preferred frame. And the data I'm talking about is that I'm familiar with is just regarding time dilation, or more accurately, clock retardation, or perhaps even atomic process retardation.
Yeah. Okay. Yes, a lot of the time, the physicists seem to be saying there is no preferred frame, but then they go ahead and use one, just deny that's what they're doing. I think a physicist Spout, SMOOT, believes that Einstein's relativity has a preferred frame, and he says that people who say it doesn't have a preferred frame don't properly understand it. So you've got this disagreement all the time among these physicists, and a lot of the time they're just totally confused, and they don't explicitly state that there is a problem in interpretation of what they're talking about.
Right. Let me add that if you know Lorentz theory, and you know how Einstein evolved from Lorentz theory, what he did, and I wrote a paper on that, was accepted and published by the Institute of Physics, IOP. What he did is make every frame act as though it was the single preferred frame.
Yeah.
So you now have an infinite number of single preferred frames, which is an inherent contradiction within special relativity.
But Einstein doesn't write very clearly as to what he means in his papers anyway.
Yes.
So he's when his 1905 paper, he is interpreted as discarding the ether, and it's very hard to understand what he means when he says that. But he seems to be, in the particular paper he's talking about, he's saying he's not going to use. It seems to be what he means is he's not using an ether frame, but he doesn't explicitly state that, and so it seems to be he's substituting inertial frame for an ether frame. So, and in the bad way he's writing, that leads to utter confusion as to what he's talking about. So his paper is very bad on explaining things, and it's very bad on the mathematics as well. If I'm carrying on with these talks, I'll be dealing with some of the mathematics he's got in his papers. Where people have gone through his papers and pointed out numerous math mistakes in his derivations. Okay, thank you.
Now, what would you say to Andrew about this comment? Because we only ever use special relativity in nuclear physics, not your ether theory. For example, you just commented that it acts as if it were in some preferred frame like an ether. But what would you say about that?
Well, as I pointed out, that there are physicists who believe that relativity has a preferred frame, and there are physicists who believe it doesn't have a preferred frame, and the preferred frame is a substitution for the idea of the ether frame. So when these people say they believe in special relativity and it agrees with experiments, really they're not addressing the issue of are they believing in the preferred frame or not believing in the preferred frame. So they can write all their scientific papers on these sorts of experiments, but it's totally ambiguous as to what they believe relativity is when they write down those papers, because they're not going into explanation of the theory. They've just left it. They've just gone by Einstein in 1905 and built upon that and made a complete mess as supposed to be what's happening as to what the theory means.
Yes, let me add one thought. I can only speak regarding the data for time dilation / clock retardation phenomena. But there, the physicists think they are using special relativity because the equation looks the same.
Yeah.
But rather than relative velocity between inertial frames, the meaning that works and is consistent with the data is that it's absolute velocity with respect to a single preferred frame. And I don't claim that that is the ether frame. Happens to be that it would be the ECI frame could be seen as the non-rotating gravitational field. So it could be that it's velocity with respect to the gravitational field. But the evidence is crystal clear about it being a single preferred frame in this area of time dilation / clock retardation. So I don't know what data Andrew is most works with most of the time, but that's a case of someone thinking that they're using special relativity, but they're actually using the data confirms that it's a single preferred frame, and then if you try and use it with other inertial frames, you'll get the wrong answer.
Now we do also have Stephen Gift here. So he gave his presentation last week. So how do you feel that his contribution works into all this? Because he has his own set of transformations, the stellaric transformations, which he prefers.
What are you asking me? Sorry.
Well, both of you really.
Okay.
Nick
So,
or Roger.
I go mainly by what Einstein writes about things, and there's utter confusion in Einstein's writing. And you can go back to the 1905 paper of when he started special relativity, and Einstein, when he wrote that paper, he only talked about one way of synchronizing clocks. And so I think with Stephen Giff, he's talking about other ways of synchronizing clocks, but according to Einstein, he didn't look into that issue. So you can then interpret it that Einstein is allowing different ways of synchronizing clocks, or he's saying there is only one way of synchronizing clocks. And it's a sort of like, it's the ambiguity issue again. And that goes through all of Einstein's relativity. You can start arguing over what is supposed to be meant by it from Einstein. So Einstein did not deny different ways of synchronizing clocks, and Einstein did not deny different ways of doing the transformations. So there were just issues that Einstein did not seem to look into. So when you bring in all that, are you then bringing in a different theory, or are you just adding on to what Einstein has already given? And that's just more arguing.
Yeah, let me add 2 points. I think of Einstein as a critical thinker because he listened to critics, and over time he changed his view. Like in, I forget it was 1916 or 1918, it's pretty well documented that he was concerned about the criticisms of the twin paradox claim in his 1905 paper, and he reversed himself on that.
Yeah.
And said that's incorrect, and came up with a different explanation. However, the rest of mainstream physics, majority stuck with saying that the twin paradox claim was correct. Now, the other thing I'll point out is that because between Lorentz's preferred frame theory and special relativity, if you use special relativity in the preferred frame, you'll get the correct answer because the equations are the same. In addition, there are certain things that are Lorentz invariant, and for those things you can use special relativity and get the correct answer. And it turns out for particle collisions that the interpretation of particle collisions are Lorentz invariant. Normally they wouldn't be, but if you put the constraints of conservation of momentum on them, then they are Lorentz invariant. So there you could view them for different inertia frames and come up with compatible predictions of what would happen, or correct predictions from your frame's point of view.
Thank you. And when Einstein changes his mind, that unfortunately creates more confusion, because then you've got what you originally said, and then later his revised thoughts, and then later on further he can change his mind again. So you've got all the confusion created by him changing his mind. It's sort of like some people want to go by what he originally said, and other people want to go by what he revised, and that is just another mess made in this physics. And if you go on to the ether issue, in the 1900, for example, the ether issue, in the 1905 paper on special relativity, the first one, he seems to be denying the ether, but then in 1920 he seems to be given a talk where he's bringing back a type of ether, and so you kind of like, oh, what view of relativity should you have? Should you have what Einstein says in 1905, or should you have it by what he says in 1920? And then after 1920, he seems to change his mind again. So you've got all these changes of mind, and that's making relativity not properly defined theory. From Einstein, you can't go to Einstein and say, this is the theory of relativity, and it's cast in stone as to what the theory is, because no, he always changes his mind. So which version do you go by?
Now I'm curious for Don Lincoln's video that was being shown. So is Don saying that he can explain the twin paradox, that by using relativity he can come up with the situation where only one twin is older than the other? I mean, was that the point of this video, that he could prove that that is true?
As per all these, there are different solutions to the twin paradox, and Don Lincoln gave his particular solution to it, and I can't remember offhand what it was, but you had this video now where it's criticizing Don Lincoln's solution. So basically, it explained in there, and it just gets into a confusion of mathematics. Ideally,
you know, the strange thing to me is that you know, the purpose of say a paradox is to show that a particular theory is just simply incorrect. So these people are the, you know, solutions of the paradox are to show that that it's not a paradox, but I don't know. Isn't the proper solution?
That's the problem you've got in relativity. You've got all these paradoxes. You've got the Barnacle paradox, and the twin paradox, and loads of others. And the idea of a paradox means there's something wrong. And so if you normally present a paradox, you're saying that something is wrong. So when you say it's a paradox in relativity, it should mean relativity is wrong. But the people who believe in relativity don't accept that the theory is wrong. Instead, they come up with what they say is the solution to the paradox. But they just give numerous different solutions, and so they're just creating a mess. It's them not accepting when they've got a paradox, meaning the theory is wrong.
I mean, it's a bunch of excuses and baling wire and duct tape to try and save what is fundamentally a wrong theory, especially based on what Nick is stating experimentally. You know, other people in the comments have stated that, well, there's no paradox when you do actual experiments. You know, when we send clocks around the world in airplanes, you know, there's never any case where both clocks are older than the other clock. That never happened. We find that it's consistent with the Lorentz theory with preferred ECI frame is what we find.
Yeah, I try to explain there's the problem in the education of teaching the theory. You need the theory properly defined, and they haven't done that. It's just total mess of different opinions. And then when they say that it's been proven by experiment, what have they proven by experiment? Precisely define the theory that you have proven by experiment is what they need to do, but they don't do that. They just say, oh, this experiment proves the theory. But what? You haven't precisely defined the theory. So the experiments are worthless.
I mean, to prove relativity, you would have to have at least two things in motion, right?
Yeah.
And most of these experiments only have, you know, like the one thing, like you have an accelerator. You've got one muon going around. And but in order to prove relativity, you'd have to use, I don't know, like two muons and show that that the frame of the one muon is just as good as the frame as the other muon, that both are older than each other. That would be the proof of relativity, right? But of course, that doesn't happen.
Correct, right? Because you can't travel at the speed, but if you're on the Earth observing the muons, they're going at a certain speed relative to you. You can't suddenly have a laboratory going at the speed of the muons. You can't actually test the theory. It's all theoretical a lot of the time. So it's sort of unanswered. They haven't defined the theory properly, and actually you're just dealing with a theory, theoretical predictions most of the time, which are left untested.
Well, here's an interesting comment, which I've not heard before, which says that all dialectic experiments do is prove that time is invariant because all clocks are visible at the same time before and after experiments, meaning they all experience the same time interval.
Not correct. No. GPS says no, that's not correct. The satellite clock rate differs from the Earth-bound clock rate.
Yeah.
But he's just trying to say that time is absolute. I mean, this or is this about, it's clock dilation and not time dilation? So
Yeah, it's clock retardation as opposed clock slowing as opposed to time dilation, right?
because I think, Roger, in your slideshow, you had the list of the controversial points, right? I think that was probably one of them, right? Is it clock dilation or is it time dilation?
Yeah. So is it just the clocks that are faulty and not working properly together, or is it actually an effect on time itself? I mean, that could create a lot of confusion, and that's not really clear in the literature, I don't think.
But people like Andrew think that there is no need to educate people on the theory of relativity, since everybody obviously agrees on it.
Well, no, they don't. When you start to interrogate the physicists, they are saying different things. They have different opinions, but that's not going into the scientific papers a lot of the time. So you can have person A, person B, and so forth. They write a scientific paper and they say, "Yep, relativity is confirmed by experiment," but they're not. They have different opinions upon that theory, but which is not going into the papers.
Yeah, here's another comment about the experiments, right? Is that not many have correctly illustrated the experiments to describe with the correct frame, light, clock, direction, and so on. Everything tends to get dumber down, right?
Yeah, when you look at Einstein's paper, the first one on relativity, 1905, there's a lot of things to argue about. So you've got total confusion from the very beginning.
Well, speaking of Lorentz, so I pointed out that, the Lorentz factor or gamma factor, primary.
The Lorentz relativistic factor.
Yes, it's a relativistic factor. It's got relatively pasted all over it. Is a primary formula for calculating time dilation. And so is that really from Lorentz and preferred frame theory? Because Andrew says no.
Well, Nick has explained that Lorentz.
Well, the Lorentz factor as used in relativity is not the same as Lorentz theory.
Yeah, the Lorentz factor is used differently in Lorentz theory to what's used in relativity most of the time.
And they'll sometimes agree if you're in the preferred frame or if you're looking at something that's Lorentz invariant, like in the twin paradox. The total difference in the net proper time accumulated is Lorentz invariant. But how that time accumulates, it's very differently explained in Lorentz theory than in special relativity.
Yeah.
And the same thing goes with a lot of particle physics when Andrew says no ECI frame is necessary for particle physics. Yeah, I'll agree with that. However, when he said particle collisions are only invariant in a certain reference frame, I know that to be not true. Let me give an example, since maybe Andrew can understand this general point. Ron Hatch was not only sort of the expert in the GPS data, but he also knew very well the BBLI data and the data from pulsar stars and NASA data. So he went to NASA and he talked with the physicists who were calculating rocket trajectories and whatnot. They're traveling in interplanetary space. And he asked them, and they claimed they were using special relativity. And Ron pointed out that no, they were using a single preferred frame, namely the solar barycentric frame. And they said, oh, well, yeah, we use that because that's how the numbers work out. If we use a different frame, we'll send rockets off course and they'll crash into the planet or mess it totally. but they were still convinced that they were using special relativity. So that's think of that as an analogy to what theory you're really using in particle physics.
Okay, thank you.
Now we do have some people commenting about the ECI frame, that it's, say, a non-inertial, and perhaps that, it's actually an accelerating frame. So how does that screw things up?
Well, if you're dealing with special relativity, ideally you are dealing inertial frames, which means you're dealing with constant velocity and no acceleration. So you're either trying to approximate the experiment approximate the experiment as being in an inertial frame, and really it's in a non-inertial frame, or else you're adding more mathematics onto it and having the acceleration effect added on.
I mean, I suppose my comment on this would be that, in spite of we may have these, it's true that, ECI is not a non-inertial frame,
Yeah.
and subject to acceleration and all this other junk, but yet the experiment's treated as if it were a geometric frame.
Yeah.
That
I have a point on this. First of all, Andrew is being very non-relativistic and anti-mainstream on his statement. Relativists consider the ECI frame to be an inertial frame because its orbit around the sun is due to gravitation, and gravitation is not considered as the force, and therefore it's called, within relativity, it's called an inertial frame. But the experimental data says that the inertial frame is a total red herring when you're talking about velocity phenomena, velocity of related phenomena, like in particle accelerators, as the Wheeler's book on gravitation notes. The effect is, the velocity effects are due to instantaneous velocity and have nothing to do with acceleration, except how acceleration changes instantaneous velocity.
Yeah, there are twin paradox. Some people offer twin paradox solutions where they bring in this idea of instantaneous acceleration, and then they try to ignore acceleration by doing that. It's an even more confusing mess then. No. If we go on that person, Andrew is saying there's no preferred framework. That's his opinion.
Well,
I'll
agree with him.
Other physicists have said other things. That if you go by Einstein, in his 1905 paper, he seems to be saying there's no preferred frame, but later on he seems to change his mind. Is Einstein changing his mind again?
Yes, Andrew, I think virtually everyone will agree with you on that statement, except a few relativists.
Yeah. Some people who believe in relativity believe in preferred frame.
Yeah.
Although I would point out that, yeah, we totally agree that no special frame exists in special relativity, yet, as Nick points out, in order to get the correct answers in your accelerator experiments, you do have to use a preferred frame.
Yeah, not for all experiments, but for certain ones that are non-invariant.
So for those accelerator experiments, that would rule out special relativity. So you couldn't possibly be using special relativity to come up with the correct results for your accelerator experiments. I mean, that's kind of the ultimate experimental proof. This is how you separate the men from the boys. This is how you tell truth from fiction.
Yeah.
Which is that you do have to look at the experiments, and you do have to go by what they say. And if special relativity says no preferred frame exists, I mean, people express this very strongly in saying that, there can be no preferred frame.
Yeah.
But if indeed, like things like GPS intimately depend upon that occurring happening, then once again, that it'd be a disproof of special relativity. So we like it when people say that there's no preferred frame, because then we can show that, oh, yes, experimentally there is. That alone is enough to disprove special relativity.
Ideally, but somehow or other, people who believe that there's no preferred frame carry on believing it anyway.
By the way, I don't think that there is a single preferred frame for all phenomena, because using the term frame is a little misleading. It's really interaction between two physical entities. So when we talk about clock rate slowing, it's an interaction between the clock and whatever the preferred frame represents. Like it might be the ether, or it might be the gravitational field. So like phenomena that are purely electromagnetic, it may be the local dominant electromagnetic field that is the preferred frame.
Yeah, I mean, I do bring the point that actually Einstein 1905 was on the electrodynamics of moving bodies. It wasn't actually about relativity. The main problem he was worried about is that if you have a magnet and you have a wire, then if you move the magnet, you get a current, but if you move the wire, you get a current. And he was talking about ultimately why that happens, right?
Yeah,
how does the wire
motion
moving?
Yeah.
Although that seems to get completely lost in the whole thing. Everyone then started talking about the twin paradox and clocks and length, but really that problem is still outstanding, which is is it the wire that's moving? Is it the magnet is moving?
Yeah.
That make any difference which is one is doing?
Yeah.
Whatever, because I have my own, for example, theories of how this actually works. And what is moving actually does make a fair amount of difference, but you have to have some physical theory for how that works.
That's relative motion, and in the twin paradox, you've got relative motion again. You've got the twin.
Yes, but instead of a magnet and a wire, you have two spaceships.
Relative motion between them. So it's relativity in the sense of relative motion. Something's moving. What's happening relative to the thing that's not moving, and it just turns into a complete utter mess. With the first paper 1905, he's not dealing with the gravity. That comes later, about 1915, with this general relativity.
Now, getting back to the whole paradox question, so Andrew asked the foundational question of what paradox is that ether model solving? Yeah, but as Nick says, it could be an ether, or it could be a gravitational frame, or it could be, anything that sets up a geometric frame. Maybe not necessarily ether. But, Andrew is still confused about what paradox is this solving.
With the twin paradox, it does look like you're dealing with the preferred frame, because you've got the astronaut leaving Earth and then coming back to Earth, and there's a time difference. You can argue it's not a time difference, it's a clock difference. But the clock.
No, I think it's more than that. I think in order to get the paradox, you actually have to show that it can't logically be true. I mean, the twin paradox if we get to the root of it, it's saying that you have two observers and the clock is older on both of them.
That's it if it's relative.
That's the paradox.
Yeah.
Clock A is older than clock B, and clock B is older than clock A. That is what special relativity tells you must be possible, right? And that is impossible, right? So I would say that what is the paradox is being solved? Well, paradox is being solved that if you had a preferred frame or an ether, whatnot, that you should come. That cannot happen. It's either clock A is going to be older than clock B, or clock B is going to be older, but not both at the same time.
That's
so
it.
This is how we're solving the paradox, and we're providing something which is actually more experimentally confirmed. For example, the closest we can do to this was like in the Happy-Keating experiment, and while there's a lot of controversy over that, you sent two clocks, one on Earth and one on going west and one going east, which is exactly the twin paradox situation. And we find that no, the clocks, two clocks are not older than the other. Clock A, clock B, and clock C all read different things.
Yeah.
And one is older than the other, but in no case do we have two clocks being older than each other.
The two clocks being older than each other doesn't happen.
Yes, so that's
one clock older, but not the other one.
The paradox, right?
Yeah. So you haven't used so the solution is to not use relativity. It's to use the preferred frame.
And then some other people are throwing some other things like the grandfather paradox.
Oh, the time travel.
Which is a time travel paradox, right?
Where you get backwards in time. I think we're not onto that. We can't even.
But I think that's another example of a paradox. That if you could travel back in time, then you could kill your grandfather. But then how could you do that? Because you would never exist, right? So once again,
there are people that believe you can travel backwards in time from Einstein's relativity, and then there are people who, I think it's Professor Stephen Hawking, tries to come up with excuses or something like
there are people, but I don't think we necessarily want to get into that argument. But
got a hypothesis there's a censorship going on that you can't actually do it. So that's another area of confusion.
This is how paradoxes are supposed to work. It's supposed to point out something that can't possibly be true. So like if you have the theory that time travel is possible, then this grandfather paradox
comes into it,
would contradict that, right?
I think there's lots of trying attempts of believing that Einstein's relativity gives you the ability to go backwards in time, and then they come up with trying to explain that away by saying there's a multi-universe, so you're traveling between parallel universes. And I think it was Everett who dealt with that and things. So it just carries on to try to patch things up.
So the value of the preferred frame theory is that, Franklin just said about you can't have clock A slower than clock B and clock B slower than clock A, but then someone may counter that and say, oh, but the experiment shows that half-life slows down, half-life decay slows down, and so that confirms special relativity. But the preferred frame just gives a better or a logically consistent, non-contradictory, not leading to a paradox, solution to that data, a better physical explanation for observing clock retardation. That's the value.
There's other comment here, which is that when we run experiments that test the twin paradox, such as Happy-Keating, like I just mentioned, no such paradox manifests itself, which is correct in nature, and the results are consistent with special relativity. Now, is that true? The results are consistent with special relativity because I think special relativity, if you did the Happy-Keating, then it should predict that the atomic clock A is older than atomic clock B, and atomic clock B must be older than atomic clock A. We do not observe that. So,
Right. They're consistent only because they just look at clock A.
I mean, I would think
Namely the lab clock. They never look at the muon's clock to see if there is symmetry or asymmetry.
Yeah.
That's the problem. Yes, it's consistent because you only look in half of the data and you ignore the other half,
well, in order to
which is logically impossible to agree with special relativity.
And the other issue,
like that, you have to have two things that you're measuring against each other to show that it's symmetric.
Right.
yeah,
It's the
but it's
symmetry
not
that
doing the experiment.
makes special relativity, right?
And that's what GPS finally did because it had a super precise clock, so it could measure at non-relativistic, could compare clocks that were traveling at non-relativistic speeds with respect to each other. And they find that if clock A runs slower with respect to B, B will agree that its clock is faster than A. So it proves, as Franklin says, that
And the other issue was about the conservation of relativistic mass and such. I did a video a long time back about this. Physicist Don Lincoln, he was arguing there wasn't any relativistic mass. So it's another area of confusion, but not dealt with in this particular video, but an earlier video.
Now, some people are asking Andrew about, what experiments he's talking about. Now, I have no idea. He apparently does a lot of things with neutrons. So, it's like the full time for the spallation neutron source at Oak Ridge, which sounds fascinating, but I really have absolutely no idea what that is. But once again, say our criticism is that you're only using like one half of, say, the non-relativity part of relativity, which is the one event, one object version of it, which is assuming, say, a laboratory frame. In order to prove relativity or actually even use relativity, you would have to be dealing with at least two neutrons and showing that it didn't matter which one was being accelerated and which one was apparently stationary, I guess. But I don't know. I don't know. But that's, an interesting point.
Okay. Yeah. Thank you.
Now, we do have a bunch of other people in the green room. So, we've got James and Carl.
We've got a hand up.
And, we would invite you if you would like to chime in on these topics.
Okay.
Raise your hand or something like that. And we would happy to have you. Okay, looks like James wants to say something. Okay.
Hello, hi. I just like to offer the view that theories do develop, and that's sort of a normal thing. It seems like the premise of Roger's and others' presentations is that it's problematic that theories develop or change with time. And I would rather suggest that in the scientific community, the normal is that theories do develop over time. And so that what might be worthy of more attention is a case where theories don't change over time. Furthermore, along the same lines, disagreements among investigators are normal. So that if the premise of a presentation is, as today, for example, that two investigators, this Lincoln, Dr. Lincoln, and the other fellow, the other young fellow, disagree on something, well, that's normal. I mean, that's not something remarkable in any manner, shape, or form in science. Experts and investigators in all fields have their own points of view, and the common normal situation is some degree of disagreement and debate. And thirdly, where a reviewer is reviewing something such as the development of or changes in the theory of relativity and disagreements among investigators, one might consider that that's only the first step to present that things have developed in a certain way, or that there are certain disagreements. The next step is to marshal experimental data as to which of the two options or investigators, or perhaps neither of them, are correct. In the case of today's presentation, is Dr. Lincoln correct, or the other young man correct, or neither of them? And that is just sort of it seems like the point is that here we have two people who don't agree, and look, that's sort of interesting. Well, no, it's not interesting. The fact that people disagree is the common normal situation in scientific endeavor. So those are a few points that I just wanted to throw into today's discussion. Thank you.
Well, thank you, James. Am I back on? What you're pointing out is there is disagreement, and they're not agreeing about relativity, but it's also a mess. When they develop in relativity, it is a mess. It's sort of like, what precisely have they changed? They're not making it clear, and when they're writing up experiments, they're not really making it clear about what they believe the theory is that they're testing. And there are great disagreements, like some people believe there was a preferred frame and some people believe there's not a preferred frame when they start arguing over relativity, and they're not really making that clear in the experimental papers they're writing up as precisely what they believe on issues like that. So the development of the theory is a mess. You've got the beginnings of the theory from Einstein, and trying to make sense of what he's saying at the beginning is a mess, and he changes his mind, and then it's not clear as to why the physics establishment have taken a certain particular point of view from Einstein and not another point of view from Einstein. So all very well developing a theory, it's they're just making a mess of that development, and that's the way it is. And I forget what the other point was. Oh, you want, yeah. I was pointing out, it's all very interesting that these two people are disagreeing about relativity in the case of the twin paradox, and that's something that they don't normally like to openly show. I've gone to physics conferences, and they will disagree in the physics conferences about things. They verbal talk, disagree, but when it comes to writing up the science papers, they don't put any of the disagreements into that science paper, and they all act like they're believing in the same thing when they're not believing in the same thing. So it's the not openly admitting to the public that there is disagreement is the first hurdle, and when you over that first hurdle, yes, the problem then is to decide who is right about relativity, but at the moment they're trying to block that by pretending there isn't any disagreement.
Now, David is asking, I think, this very foundational question, which is, when we're talking about these various frames, frame A, frame B, ECI frame, what is this frame physically? I mean, do you have an opinion on that? I mean, is it even a physical thing?
Well, in the case we've dealt with here in the twin paradox, there's the frame for the person who's staying on the Earth, and there's the frame for the person who's traveling off in the spaceship. And that's the two frames.
And also, I noticed you've come. You're very dark. It's like your lights have been turned off.
Yeah, I think it's gone dark here now.
I guess, yes. It looks a little bit, I don't know, spooky. But
yeah. I don't know. Yeah. Oh well.
It's all right. I just thought I'd as
Yeah.
opposed to the bright background of me and Nick.
Yeah.
But
Okay.
I could take a stab at what is a frame, because the frame might
Yeah.
not be something physical, like you said. The frame is just defined as the geometric space around person A, and the geometric space around the person B who's in the spaceship who's traveling. In which case, there's really nothing physical about that. That is just. But if you are a Lorentz preferred frame person, then I think this definitely has some relevance. And and as Nick has pointed out, that frame could be something different. Like if we do experiments on the planet, say the planet Earth, we would tend to use the ECI frame to get the correct results. But if we are sending space probes out into the solar system, then NASA has found that they have to use the sun-centered frame to get the correct results, right? So it's like, that's one thing, is that like, well, how can there be a preferred frame when there's two preferred frames depending on where you're at, right?
In the math, you can choose which frame you want to prefer.
Yes, but in order to get the correct results, there are at least these two.
Yeah.
And I would say that physically, this is why I say I would prefer an ether frame, because I can explain this if there was something physical like an atmosphere or like water.
Yeah.
If you have water can be in different kinds of motions. You can have water flowing by in a pipe. You can have water sitting in a lake. And if you were to do your experiments, you would get different results depending whether you're in the pipe or whether you're in the lake, right? Just like you get different results depending on whether you are in the Earth influence or whether you're in the solar influence, right? If you thought of space as being like water, then you could think of the Earth being surrounded by a sphere of stationary water that the Earth is spinning around. And when it goes around the orbit of the sun, it's like dragging, say, its bubble of water around with it. But that whole thing is still immersed in another bubble that surrounds the entire solar system. And then when you send your individual space probe through that, past our individual Earth bubble, then you have to start using that frame. And that frame, that would be a physical frame. So that's kind of how I see that.
Yeah.
But it's a very foundational question. What frame are you talking about, right?
Yeah.
Yeah. When we're talking about the preferred frame in this context, where we're talking about the effect, a phenomenon that affected by velocity. So it's the frame, the preferred frame is the frame from which you measure absolute velocity.
Yeah, we have Jim Marston's comment here, which kind of goes along with perhaps what you were saying, Nick, that the frame has something to do with the gravity.
Yeah.
The ECI frame, as soon as the sun's gravitational magnitude is higher, then we have to start paying attention to the sun's frame and not the Earth's, right? So that seems to have something to do with gravity, right? Fundamentally.
Right. Actually, for a lot of interplanetary travel, it's not the solar frame per se, but the solar system's barycentric frame, which is the center of mass, which is affected somewhat by large planets like Jupiter and Neptune and Saturn. So it's a center of mass, which could be considered also as a center of gravity type of.
So it depends on the position of Saturn and Jupiter pulling the center of mass.
Yeah.
And if you don't do that, then your probe going to Uranus is going to go somewhere XY you don't want it to go.
Yeah.
So that would be a very precise thing, saying that it's not a thing, but perhaps just a conglomeration of matter, right?
Let me just hark back. I had one comment about James's point. First of all, I agree 100% with how he characterizes the development theories. But what Roger, I think, has pointed out really well is that there's something qualitatively different and less desirable going on in the development of special relativity, because it's not as though they say, oh, I'm wrong in A, and therefore special relativity comes along, it's changed, and now everyone agrees with A. It's just that there are a whole baggage of different concepts that are contradictory that are carried forward together.
Yeah.
It just seems that qualitatively it doesn't quite live up to that nice ideal that James has talked about. And I thank Roger for pointing that out very, very well.
Thank you, Nick. Yeah. Relativity is a collection of different opinions, and they're not making it clear which is the correct opinion, so it's not really a proper development. It's just a mess.
How about this question? Very foundational. Quest Ion asked, what's a preferred frame exactly? What are we talking about when we say preferred?
Well, again, I think a preferred frame is an abstract math concept, but what's really happening physically, there's a preferred physical entity. And for velocity-dependent physical effects, such as clock retardation, that would be the ether. If motion with respect to the ether causes clocks to slow, then the ether is the preferred physical entity. If it's really the gravitational field, that's velocity with respect to the gravitational field, causes clocks to slow. And that was Ron Hatch's preference and my preference. But maybe it's the gravitational field also acts like the ether. So, but it's basically when you're talking about how one thing like a clock is affected by velocity, the preferred frame represents the physical entity where motion is reacted by relative velocity with respect to that single physical entity.
Okay, we've got Harry. Go ahead, Harry.
Okay. Let's go back to the video at the beginning. The guy that was objecting to what Dr. Lincoln said, he had two different frames. He was saying that we have frame A and then we have frame C, where we're defining the two different frames. Is that correct? Did I understand that correctly, Roger?
Well, I was pointing out really it's just a mess in the way they disagree about things.
Well, I'm just asking, did I understand the video correctly? Is that what he was doing in the video?
He had lots of frames and he was trying to make it more complicated than the way that Don Lincoln was dealing with it.
Well, the problem is, essentially the problem is that in mathematics, if you take two different frames of reference at the same time and try to reconcile them in the way that was done by Dr. Lincoln in his video, you can't do that and you can't get a correct answer. That's the problem. That's the whole problem with trying to reconcile the twin paradox.
Those who believe in
because you can't use two different frames at the same time to do your calculations. When you do that, you don't get the correct answer. That's the whole point.
Those who believe in relativity wouldn't necessarily agree with that.
Well, they're trying to reconcile the fact that the mathematics doesn't work. That's what the paradoxes are. The math doesn't agree with the physics that they've assumed. Okay, so what Einstein did was he assumed a postulate, the relativity postulate, and then tried to make this theory that he had based on the relativity postulate, and it doesn't work. You can't have multiple reference frames in the same time and try to do calculations that make them agree with each other, it doesn't work. That's what produces the paradoxes. So there's a mathematical mistake in trying to make the principle of relativity that assumes multiple reference frames agree with mathematics, which doesn't allow you to do that because it disagrees with the mathematics and the principle of relativity in the same theory. That's what this is all about. Do you understand that?
Yeah, unfortunately, the people who believe in relativity don't readily accept things like that.
Well, that would mean they'd have to abandon their theory, which they don't want to do.
Yeah.
Okay, so they've got a bunch of so they've got a bunch of experiments where they test in one frame only and say, oh, it agrees with the special theory of relativity. But then when you when you do these thought experiments, like was demonstrated in the video, you have to have two different frames, okay? And you do calculations in one frame and calculations in another frame, and they never agree. That produces a paradox. So you have a conflict between the mathematics and what they are assuming as the physics principle that applies. Doesn't work. That's the whole point.
I don't think the point is being gotten. See, Andrew says that special relativity is a theory that accurately describes space radiation, particle physics, nuclear energy, astrophysics, etc. That's a part of the reason why I've jumped onto each of these.
If you take away the relativity and just call it the special theory, you're okay. But if you put in relativity, it doesn't work because the math doesn't work. It's defective. You can't have multiple frames at the same time. That doesn't work in the math.
Yeah, but people will point out that
if you take one frame and you do all your calculations in one frame, so essentially what people have said here, this has been discussed over and over. NASA uses one frame. If you use one frame, you can make the Lorentz transform work. If you want to do multiple frames at the same time, it can't work because it violates theorem of mathematics. The mathematics doesn't give you a correct answer when you do that.
So do we have imposter syndrome here? Special relativity has been the imposter for Lorentz single frame theory that works accurately. And
no, the problem is when you use the word relativity. Relativity means you're using the relativity principle, which says that you have multiple frames of reference in which the physics is the same. If you try to use that principle and put it into mathematics, the math doesn't work anymore. So the problem is you've got to try to, the math doesn't work given the principle of physics that you're trying to make work in the math. And the math doesn't work, it produces paradoxes. That's the problem. And then so people don't want to recognize that this is what happens.
Yeah, they don't want to recognize it. There's a conflict in the mathematics and what they're saying.
The math that goes with the principle of relativity doesn't work. That's it. That's the bottom line.
And the equivalent physics statement to what Harry's math point is that if you're going to talk about physical effects rather than just observed effects, you need to have a preferred frame. Like velocity dependent physics depends on using velocity with respect to a single preferred frame or single preferred physical entity.
Right. Well, so this Castro guy says, we proved special relativity works in our nuclear experiments, but they use only one frame of reference, the center of gravity frame, when they do their calculations. So they're using only one frame. Special relativity asserts that has to be true in multiple frames. Okay.
Right.
When you do the multiple frames calculations, you get paradoxes because the math doesn't work.
All right. And Andrew made a statement that is in my area. He says, Andrew says, I looked at some 10 years of GPS data when analyzing data at NASA, always with the relativistic transforms. Now, you are arguing with the world's expert on GPS, Ron Hatch, who says that statement is not true. It's not a relativistic transform that you were using. It's a preferred frame transform, the original Lorentz transformations, which are preferred frame. That's how it's correctly interpreted in physics. It's definitely not relativistic. And GPS wouldn't work if it was built on a relativistic model and they used different inertial frames because of their thinking that any inertial frame is fine.
The math says you can't use multiple frames because it violates the unique identity theorem of mathematics. So algebra, linear algebra, the systems of algebra that mathematicians use assumes you can only have one frame of reference at a time, not more than one, only one. It's in the math.
Yeah.
So you can't take a physics principle that assumes I can have as many frames as I want and try to solve a math problem because the math says you can't do it.
Mm-hmm.
This is not complicated.
I don't think they mess up when they do the maths and the words. There's confusion between.
Well, let's go back to the video at the beginning.
Yeah.
Let's go back to the video at the beginning. What he did was he said, well, I'm going to take a frame that starts at time 0 for A, the observer A, and then I'm going to take time 0 starting again for another observer at C. So now you have two frames. He's got an observer at A that time starts at T equals 0, an observer at C that time starts at T equals 0. And you can't make them agree with each other because it violates the principle of mathematics that's in the unique identity element theorem. And so you can't reconcile them. So the guy concludes that Dr. Lincoln's attempt to resolve the twin paradox is false. And he's correct.
Okay. Thank you. Cheers. Yeah.
Let's see here. Now Andrew says he's in the waiting room. Is he under Andy? Now, I have no video feed from him, but I'm going to have to presume that he is. So I'm going to put him up for a second, and you're muted.
I think if he's Andrew Castro, he's pretty
if you want to say something, you can try.
Mm-hmm.
Oh, he's muted.
I'm not 100% sure.
Yeah.
He has to unmute himself.
Yes, if you're sitting there. There you are. Okay, great.
Hey, can you guys hear me?
We can hear you.
Yes.
Good. Thank you.
I mean, I just wanted to clear up some confusion I think you guys have, especially in terms of this notion that there's a preferred reference frame in relativity. I mean, there is no preferred reference frame.
We all agree.
I disagree.
In terms of quantum mechanics and nuclear physics, we're typically doing everything in the center of mass frame. That's the easiest frame to carry out a calculation in. And then once you build an experiment, that's going to have its own frame. You don't know what that is when you're carrying out a theoretical calculation. You have to wait for somebody to design an experiment. And then once they design that experiment and build it, you'll have an idea of what their frame is, and then you transform into that frame. But that's not dependent on an ECI frame or solar-centered frame or anything like this.
Right. It depends on the context of the experiment. For GPS, the ECI frame is required. For NASA interplanetary travel, not right near the sun, the barycentric frame is required.
But you're not violating you don't violate the unique identity element theorem, do you? In any of your calculations?
What's the unique identity theorem exactly?
Basically, it's that you have to have a preferred frame.
No, there's no preferred frame.
That's just denial. You're using an unstated preferred frame.
So I mean,
you're
like,
not treating the
It's
frame
just
the same.
it's just semantics.
I mean, I guess I'm also curious, like,
It's all just
maybe
semantics.
we
So you're confused,
can-
Andrew, because of semantics. Get the semantics correct. Understand what's being said.
Well, I mean, maybe you can give an example. Like, if I'm looking at a nuclear decay, what frame should I look at it in, and what frame should I transform it in? Like, if I'm looking at, say, just a very vanilla pion decaying into 2 photons, what would the energy be? How would you guys calculate that? Because I would only use special relativity.
We're not doing this.
To do
This
that.
isn't
And that
our
would give me the
problem.
correct answer.
Yeah.
That's
What
red herring.
frame?
The red
What
herring.
experiment
You
are you
already
doing?
know the answer. You're using a frame that works, but you're only using one
Which
frame.
frame
You're
is
not
that?
using more than one frame.
Would your calculations
If I look at a pion decay, that decay looks different in different accelerator experiments versus the center of mass calculation. A pion decaying
Only
into 2
one frame
photons
at a
would-
time, right? Where are you using more than 2 frames of reference at a time? Never.
when
You can never use more than 2 frames at a time.
when I am
because the math
measuring the
doesn't
pion
work.
decay, when I'm measuring the pion decay, that does not look the same as the center of mass frame. The laboratory frame would be measured in an experiment, while the center of mass frame is what I would calculate it in, and that's how I'd identify that interaction in an accelerator.
different physics phenomena, as I mentioned earlier, would have different preferred frames. It's a single preferred frame for the
What
phenomenon.
would the preferred frame of that be?
Well, if you're measuring muon decay,
No, let's just say a pion
no. Well,
decay
let me answer within the. If you're measuring muon decay, it would be the ECI frame.
When? And what experiment would I do that in?
Oh, well, that's what John Field, the expert on muon half-life decay at CERN, has written about. That it's
And
the
how'd
ECI
you
frame.
verify that? He says it's one preferred frame, but how'd you verify that?
From
What
the
did he
data,
say?
he
What
says
did he say the frame
if you
was?
take another frame as your preferred frame, like special relativity says, then you get the wrong. It doesn't agree with the experiment.
What would that second frame look like?
Well, special relativity says you can choose any inertial frame.
Okay,
But if you choose,
what would that second frame that doesn't work out then look like?
well, special relativity doesn't say what it looks like, and if
you had to have done a transformation into that second frame.
Mm-hmm.
So you're telling me any frame would make this muon decay not work, but you can't name it.
The
You can't
laboratory
tell me
frame
any
is
kind of
really
transformation,
named.
what it
In the
looks like, or
mathematics,
anything.
If you've got a frame A and a frame B, such as in the
What is
paradox,
frame A that would make a muon decay work?
then you're choosing which one you can take as the preferred frame.
Okay,
And
then
so
put some
the
meat
twin
on
on
it.
the
What
Earth
does
is
frame A
treating
look like? What
twin on the
experiment
Earth
are
is
you looking at for frame A? And then what
Frame A
transformation?
should be
if
the
you're looking,
laboratory.
if you're measuring clock retardation or atomic process retardation, the ECI frame, using the ECI frame as the preferred frame, the base frame, the frame from which you measure velocity, the ECI frame is the one that best meets and correlates with the experimental data.
And what experiment uses the ECI frame? And how do you know that?
Well, because John Field has written it up, and he's the
Okay, he wrote
expert.
it up, but you can't name it. You can't even describe it. Or what experiment?
Yeah, he's measuring half-life decay.
In what experiment? What and how do you know that was the ECI frame?
Because he said so in his paper.
So, but
Yeah,
you didn't
Nick,
confirm
perhaps you should put the reference, because it's perfectly reasonable to ask for a specific experiment, and you're giving him one. And he's asked for a
I mean, there's
specific
a lot of
alternate frame.
muon experiments at CERN, and they're not all equivalent. And I mean, I've known people that have done many different experiments on muons at CERN, and they're not all using the same frame.
Yeah, but
for
half-life decay,
and
the one that gets
the right answer that you can't name.
Well, I'll put into the chat. I'll put into the chat some references. Hold on a second.
Is it that finished?
I have to do a little research here.
Okay.
Although we are at the top of the hour here, so
I would be interested in knowing what you guys would think would happen.
Andrew, what your objection to is your objection is basically terminological, because you basically think
my objection is where's the data you guys make a lot of claims about only a preferred reference frame, not a preferred reference frame. You guys kind of go back and forth, it seems like, but I've never seen you guys ever present any data from any experiment with any kind of analysis on it. I think
that's your responsibility.
Andrew,
you're confusing. You're confusing the issue. This is what you do. You confuse the issue because now you're just basically confusing the issue. The point is
special relativity in a lot of different experiments, and I publish it.
The point is that special relativity has the problem that you can't do calculations in more than one frame at the same time. You get paradoxes. To define what that frame is, that one frame is, that's your problem, Andrew. That's a physics problem. I'm talking about a math problem.
Well, I mean, I thought this
the math can't be done.
The math can be done because I do the math.
Hey,
I mean, that's
you're just basically you're just playing games here. That's all you do. You play games.
I mean,
the point is being made that there's a paradox problem in relativity. You don't want to believe it.
Paradox in relativity. How do you establish there's?
Well, we've established a paradox, as we explained before, because clock A has to be older than clock B, and clock B has to be older than clock A according to special relativity. That's the simple paradox.
How do you know that's true?
Because that's what the special
relativity when we run experiments that can kind of test the twin paradox, no such paradox manifests itself in nature.
Exactly. So what does that tell you about special relativity?
It tells me that paradox is wrong, that math scenario, that thought experiment isn't valid. It's not correct.
Well, it might not be, but usually paradoxes...
Exactly, that's what we're saying.
...qualify the actual original theory.
I mean, it seems to me, I mean, like when I've talked to other physicists about this, that you cannot establish the twin paradox using special relativity, because they inherently do not have the same space-time interval. I'm not sure why you think if I have a twin on Earth and I have a twin on a spaceship, why would they have a paradox in the two clocks from those two scenarios? You need to establish that.
Yeah, that's very basic.
You just take that as granted. You say, Einstein thought up of this paradox. He might have been right. He might have been wrong. I'm just taking it as granted.
You're just putting out words with confusion. You're completely confused, and everything. You turn everything upside down on its head.
I mean, I don't understand why you're getting upset, because these are the kind of conversations I have with other physicists. You're saying like.
I mean, you seem to be telling me that physicists have their thinking upside down.
No, because we use special.
I mean, you're justifying upside down thinking.
I mean,
there's no paradox because we say there's no paradox. That's what you're saying.
No.
You're saying physicists say there's no paradox because we say so.
Well, can you establish that such a paradox exists within special relativity, or do you just take it as granted that somebody said there was a paradox?
Well, we wouldn't even be talking about it if the paradox didn't exist.
I mean, the paradox is expressed.
How do you know that the guy?
If there was no paradox, we wouldn't be talking about it.
Well,
that's the whole point of what Roger's trying to say.
I mean, even the special relativists agree that the prediction made by the paper that because the clock of the stationary person on Earth and the clock of the person moving are equivalent, and that
how do you know they're equivalent?
The Lorentz factor indicates that both of them will experience time dilation in a symmetrical manner, which means that both
that's
be older
only
than
if they are on the exact same space-time interval. Can you establish that?
Yeah, obviously,
Okay.
because they are in the same Earth. They start at the same place. It's the same interval, obviously.
I would like to see that worked out.
I mean,
Okay.
But
Let me take a.
we're out of time today. It's actually we're a bit over time, so I think we're going to have to wrap things up here. So I'm going to bring back Roger up here, and we're going to let him wrap things up here. Okay, so go ahead, Roger.
Hi, I managed. Thanks. I managed to put the light on. So wrapping it up. So what we're pointing out is when the physicists deal with things like the twin paradox, they're not all agreeing on things. And I managed to find that video where they're disagreeing. And so they're not giving a properly defined theory, a theoretical explanation for things like twin paradox. They're just going to create utter confusion by saying lots of different things. So what we really have is a collection of different opinions. And when it comes to the development of relativity, well, that's just a total mess. It's just a mess. I mean terms like preferred frame, when you look in the history of relativity, are talked about. And so when you get to what are modern physicists doing now with their experiments, what are they doing in terms of the old idea of preferred frame? That they're not explaining things properly. It's all just a terrible mess, and they're just blundering on and blundering on. And then the education system, well, that just blunders on. It start telling you there's things like relativistic mass, and then we have physicists who are supposed to be working on it, like Don Lincoln, and tell you there's no relativistic mass. So it's all just a mess where they're just saying lots of contradictory things. And so they need to properly tell us what the theory of relativity is. And so then we know what alternative can we present to them as to relativity. But at the moment, it's just a confusing mess as to what relativity is. Einstein changed his mind lots of times. So why are they going by some of the things he says and not going by other things he says? Why have they made changes? Why are they doing all this and that? And so it's just a failure now with the scientific method, because you're supposed to present a theory, test that theory, and then compare it to another theory. But at the moment, their theory, which is relativity, is just a confusing mess of all their different opinions. You haven't got a properly well-defined theory. Thank you. That's the end of this little talk. We log off now. And next time I'll bring up more issues of problems with relativity, if providing able to. Thank you. Are you there for